There's some little part that, oh, hold on, I get the message coming in. There are some answers highlighted in pink color when we work together. The one that I mark in pink. The one I mark in pink, maybe that's something I will do further tomorrow. Basically, very likely because I didn't cover that yet. Or maybe that's for test 2. But I think you say test 1 practice question. That's, yeah, I think you need to wait until tomorrow. But by the way, those are not practice question. Stop calling that practice question. It's the old previous tests. Okay. Now here's the thing: why I don't want you to call that practice question, because it sounds like that's for you to practice only. Yeah. But it's previous test. That's actual test that I gave my previous students. Okay. It's not. You can use that for practice, but that itself is an actual test. Okay. Yeah. I don't give practice test or kind of like a mock test like that. No, I don't do that. I give you my old test. Okay. So study from that as if that will be your test. Okay. As if that will be your test. Of course, your actual test will be different from that. Okay. You use that to practice, but uh, here's the thing: when we say practice question, it means it actually has this connotation. So let's say my actual test has like 15 questions. Okay, that's in the actual test. But practice question usually has a lot more than that. Let's say the practice question will be like 50 questions, right? And then you practice from these questions. Then in your actual test later on, I will pick some problems from there. That's what the connotation of practice question is. No, I don't give practice question, I give actual question. Okay. Now let me go back, and then there's some leftover from 2.2 that I didn't do last time. I was running out of time, but this part is actually on the easy side. It's about notation. It's more about notation. Let's take a look on number 23. As x approaching -1, x approaching -1 from the left hand side. You see this negative on the superscript there. Okay, so as x approaching -1 from left hand side. So this is -1. This is x equals to -1 here. This is x equals to -1, right? Now we will approach that from left hand side. Now, if you approach that from left-hand side, what will the value of the function approaching? The value of that function approaching this, which is 2. Okay, if you approach from the left-hand side. Part B, as you approach +2 from the right-hand side. Where's +2? +2 is here, right? Now then, when you approach +2 from the right-hand side, then what will the graph of that function, what is the value of that function approaching? That's approaching 1. Okay, later on in calculus, you will learn the following notation. Like part A, they will write it this way: limit x approaching -1 of the function is equal to what? That's equals to. Okay. Now, part B, for example, the notation will be limit, oh, I'm sorry, this is from negative side. Okay, limit x approaching 2 from the right-hand side of the function is equal to what? As x approaching 2 from the right-hand side, the value of the function is approaching 1. How about part C? As x approaching 3. So x equals to 3 is here, right? Okay, now then when you approach 3, what the function, the value of the function approaching? You approach from left, approach from right. If there's no notation where you approach that from, then you approach from both sides. From both left and right hand side. Okay, now here you see that as x approaching 3 from left and right hand side, the value of the function is approaching 4. When you approach from the left hand side, it's approaching 4. Approaching from right hand side, that's also approaching 4. Okay. Now, then what if part D as x approaching infinity? So when x goes indefinitely far to the right, so you assume this is actually going to the right, going all the way up there. Okay, when the function goes to, when the x goes to infinity, then the value of the function will go to increase to infinity, right? The function goes to infinity. Now in chapter 3, you will see we say the far right behavior is infinity. It will go to infinity as you go very far to the right. If you go very far to the left, when you go very far to the left, in this case, when you go very, very far to the left, the value of the function will go to negative infinity. So that's only just notation. It's really just notation. Okay. Now in calculus later on, the notation for this will be limit x approaching 3 for the function fx will be 1. Okay. In part D, from the graph, limit as x approaching positive infinity of the function will be what? In this case will go to positive infinity. And the last part, part E, limit as x approaching negative infinity of the function, that will be negative infinity. Now let's use number 24. Let's use number 24 as our example. Part A, as x approaching negative 2. I'm sorry, x approaching 2 from the left hand side. This is x equals to 2, right? X equals to 2. But you approach from the left hand side. As x approaching very, very close to 2, then the value of y is approaching 3. Right? How about when x approaching negative 1 from the right hand side? So you go through that curve, right, the graph, but from left hand side approaching negative 1, then the value of the y is approaching negative 3. Okay. How about when x approaching 0 from both sides? So this is x equals to 0 here, right? When you approach from the left-hand side, that's approaching negative 1, the value of y approaching negative 1. When you approach from the right-hand side, the value of the function also approaching negative 1. So this is equals to negative 1. Part D. Part D, as x approach positive infinity, so when you go to very, very far to the right, what will the value of the y be as you go very far to the right? Now you see that the function going down all the way, as if you go, the further you go to the right, the more it goes down. Okay, so as x goes to infinity, the value of the function is will go to negative infinity. Now, then as x goes to negative infinity, when you go very, very far to the left, the value of the function will go up to infinity instead. Okay, now what we do here is more into notation. It's more into notation. You need to know how to read the graph and how we denote that. Now, suppose, for example, I have the following graph. This is the time when we have more issue with the left-hand side, right-hand side limit. Give me a second. Let me try to graph that. Suppose we have this example here, okay? And then I will graph it this way. So thick one, so let me graph it this way. Let's say we have that graph. Let's say we have this graph. Okay, this will be -5 here. This is -2. This is 1. This is 5. This is 3, 2, 1, 4. Okay, so let's see. As x approaching 1 from the left-hand side, fx approaches 1. So this is our x equals to 1. It's here, right? Now you will approach from the left-hand side. So the graph, as x going closer and closer to 1, x equals to 1 from the left-hand side, the value of the function is approaching what? As x approaching 1 from the left-hand side, the value of the function is approaching the value 4. Okay, but when we go from the right-hand side, as x approach 1 from the right-hand side, the value of the function will approach 1. When you approach from the right-hand side. So from the right-hand side, when you go approaching 1 from the right-hand side, then the value of the function is approaching 3. Okay. But Thomas, that's an open circle there. That's okay. That's okay. That open circle simply means that f1 is not 3. That's all it says. That open circle says f1 is not 3. What is f1 here? f1 is equal to 4. Okay? f1 equals to 4. How about when we do this one? As x approaching 5 from the left-hand side, fx is approaching what? So as we approach x equals to 5, this is x equals to 5, right? So we go approach from the left-hand side. So you follow the graph, approach x equals to 5. As x very, very close to 5 from the left-hand side, then the value of the function approaches 1. It will approach, the value of the function approach 1. That's right. That approach 1. However, what is f5? F5 is undefined. Okay, F5 is undefined. That's right. Why? Because when x equals to 5, there's no value for that. Okay. Now, let me give you maybe 1 minute to do the following. As x approaching -2 from the left-hand side, what will the value of the function approaching to? As x approaching -2 from the right-hand side, what is the value of the function approaching to? Okay, you try it. I give you 1 minute. Okay, as x approaching -2, this is our x equals to -2, right? When you approach from the left-hand side, means you go along the graph from the left-hand side of -2, the value of the function is approaching, actually, when x approaching 1 from left-hand side, it's not 4. I count it wrong, that's 5. And f1 is actually 5. I count it wrong, sorry. When x approaching -2 from the left-hand side, that is the one approaching 4. Okay, but when you approach -2 from the right-hand side, approaching -2 from right-hand side, then the value of the function approaching +2. Okay, I mark this one down. That's not 4, that's 5. This 5 here. This is the one 4. Okay, now again, that's about notation. That's just about notation from 2.2b. Let's go on to 2.4. 2.4 is on definition of functions. Now, again, I assume that you have watched lesson 7. I assume that you have watched lesson 7. Lesson 7 actually did part of 2.4. That's like the later part of 2.4, and 2.5 and 2.6. Okay, but let me go over definition of functions again. Definition. a function is a relation, or sometimes we say correspondence, from one set which we call domain to another set which we call range, such that every element in the domain corresponds to exactly one element in the range. If we take a look on the mapping, let's say this is the set of the domain, and this is the set of the range, then every element in the domain corresponds to exactly one element in the range. Let's say A corresponds to P, B corresponds to Q, and C corresponds to Q also. The restriction is on the domain that every element in the domain corresponds to only one element in the range. The restriction is not on the range, the restriction only on the domain. So once you have an element in the domain corresponds to two elements in the range, then that's no longer a function. It is still a relation, basically everything. Okay, but because of that blue correspondence, then this is no longer a function. Okay, without that blue correspondence, it is a function because every element in the domain corresponds to exactly one element in the range. Now, we say this diagram here, the mapping diagram, the mapping. Okay, now we can express that correspondence using coordinate, or sometimes we call that ordered pairs. So for example, from the mapping we see on the top, we can write it as a coordinate A, comma P, B, comma Q, C, comma Q. Okay, the first component of that coordinate is from the domain. The second component of that coordinate is to what the component in the first coordinate corresponds to in the range. Okay, so it's quite easy to see if a relation, a function from the mapping. Just look at the domain. If you see any branching from the domain, if you see any branching from the domain, then it is no longer a function. Okay, now when we have coordinates or ordered pair, see if you have same x component. Okay, if you have the same x component that corresponds to different y components. Let's say, for example, I have AP and then another coordinate AQ. Then this A is actually cheating with P and Q. That's not right. That's not a function. Okay, That's not a function. But without this a going to q, this is still a function. Now the third way to express this correspondence, we can use function notation. Now the thing is, mapping notation can be used even if it is not a function. Coordinates notation can be used even if it is not a function. However, once you use function notation, then it has to be a function. Okay, the function notation will be f of a is equal to b. Okay. A is in the domain. F of a is the output if the input is a. Okay, fb equals to, actually no, the top one, fa is actually p. fb is q. fc also q. Okay, now if the domain and range are part of or subsets of part of real numbers, then we can put them, we can put the function on coordinate plane. To be more precise, our Cartesian coordinate system. Okay, so for example, we have example 1. Let fx equals to 2x minus 1. So if we try to see this from mapping point of view, if the input is x, then the output is 2x minus 1. Okay, now the thing is there are a lot of x that we can use for this function. There are a lot of x that we can use for this function. Now then you will see, for example, when x equals to 0, let's see, f0 is what? f0 is -1, right? F2, for example, that's 2 times 2 minus 1, that's 3. What else? F4 is 2 times 4 minus 1, that's 7. F-1 is 2 times -1 minus 1, that's -3. Okay, those are some coordinates that satisfy that function, right? Okay, some x that will give us the y, but from each one of these, it gives us the coordinates 0, -1. Because the x is 0, we know that's the y-intercept. 2, 3 is part of the graph. 4, 7 is part of the graph. -1, -3 is also part of the graph. So when I plot them, -1, -3, 0, -1, 2, 3, 4, 7. Then we will get this graph. And you can see this actually a linear equation, linear function. We call that linear function because when we graph that, it looks like it is a line. It gives us a line. Okay. Now I go ahead with how do we identify the graph of a relation as the graph of a function. Okay, note vertical line test. The graph is the graph of a function if every vertical line intersects the graph at most one point. Okay, so for example, the graph of this fx equals to x minus 1, when you draw a vertical line, it will intersect the graph at most at one point. Okay, at most at one point. Now, if you wonder why vertical line test is true, now, vertical line test is true is because, why this is true? Because, remember, because each element in the domain X, the domain X, corresponds to exactly one element in the range. Right? Okay. So here's what happened. Okay. So here's what happened. If a value of X, let's say, call that X equals to A, is in the domain, then it corresponds to 1y. To exactly 1. Right? Now, what happens if that X equals to A is not in the domain? Now we say that X is not in the domain if it corresponds to nothing. So if it is in the domain, it corresponds to only one y. If it's not in the domain, it won't correspond to anything. Okay, so either way, it will correspond to at most one. Either way, any element on x axis, okay, if it is in the domain, corresponds to 1y. If it is not in the domain, it corresponds to nothing. Okay, so any element on x-axis corresponds to at most 1. Okay, that's how we know that the graph of a relation, the graph that we have is uh, the graph of a function. Okay, now that's for vertical line test. The more difficult part is actually from a given domain, a given function, how do we determine the domain? Okay, to be more precise, how do we determine the natural domain? Let me insert that word, natural domain. Oops, what happened? The natural domain. Okay. Let's say, for example, if you see that fx equals to 2x minus 1, right? For example, little example, fx equals to 2x minus 1. How do we decide what's the domain, the natural domain? Okay, now here's the rule. What is the domain first? The definition, the domain of a relation, in this case including a function, is the set of all x or real number x, or maybe all real number, I should say all real numbers such that the outcome y is also a real number. I don't really like that. The domain of relation is the set of all real numbers such that the corresponding, yeah, instead of saying the outcome y, the corresponding y, is also a real number. Okay, so if we look at this function, for example, here, think of what x that you can plug in such that 2x minus 1 is also a real number. Okay, so the domain here, you will see the domain is all real numbers. Basically, you can plug in any real number you can think of, from negative infinity to positive infinity. Okay, in general, at this point, we have this rule. We have this rule, or maybe you call that rule of thumbs. Okay, first, if the function is a polynomial, then the domain is all real number. if the function is a rational function, the function is a rational function, let's say, for example, for instance, we have fx equals to 2x plus 3 over x minus 4. Okay, then the domain is all real numbers except the zero of the denominator. When we say the zero of the denominator is the value x that makes the denominator equal to 0. Okay, so like in this case here, in this little example here, the domain will be all real numbers except 4. It's all real numbers except 4. Now, why we need to exclude 4? Because when you plug 4 into the x in the denominator becomes 0. Okay, that's what we meant by the 0 of the denominator. Okay, maybe I explained that a little bit here. The 0 of the denominator is the value the x such that the denominator becomes equal 0. Okay, now the third one, if the function is radical with even index, like square root, the fourth root, sixth root. Let's do a little example, like what we mean by even index. Even index, like for example, fx equals to the square root of x squared minus 3x, let's say. Okay, now that's even index, right? If you have that kind of function, then the domain is all real number where the radicand is at least 0. Now, if the function is a radical in radical form with even index, for odd index like cube root, fifth root, sixth root, it's okay. It's okay. We don't have such restriction. Okay, the domain is still all real number, whatever you have in the radicand. But if the index is square root or fourth root, sixth root, then the radicand has to be at least 0. We usually say that the radicand has to be non-negative. Okay, x squared minus 3x has to be at least 0. Is it okay? Now, I think only those three functions that we'll be dealing, the three types of function we will be dealing before the chapter 3. Okay, now the thing is then, suppose we have this function fx equals to square root of x squared minus 3. Then what's the domain? We basically need to solve this inequality. Okay, now then how to solve that inequality? Because it's polynomial, right? Polynomial inequality. If it is linear inequality, you can just solve it using linear inequality method. But polynomial inequality, then you need to go on with step 1, critical numbers, okay, critical numbers, x squared minus 3x equals to 0, x minus 3 equals to 0, x equals to 0, x equals to 3. And then step 2, you do the sign graph, right? We did this before. Okay, when x equals to 0, the value is 0. When x equals to 3, the value is 3. Right, and then when x, let's do a testing point, when x equals to 1, for example, we'll get 1 times 1 minus 3. That's positive times negative, so that's negative. And because the critical number x equals to 0 and x equals to 3 are odd multiplicity, then every time we jump across, that critical number will change the sign. So finally, we say the domain is, we say now the domain is all those regions that have positive or 0 sign. So from negative infinity to 0, union 3 to infinity. Okay, now let's take a look on in our textbook. If you have our textbook, let's take a look, for example, number, I will do it really fast here. Number 21. I think I did a lot of even number in my lecture. Let me do odd numbers in right now. So find the domain. Fx equals to square root of 2x plus 7. That's a square root function. What is the domain? Then you look at the radicand. It's a square root, right? So the radicand has to be non-negative. 2x plus 7 should be greater or equals to 0. But that's linear inequality, so you will just solve it like you solve linear inequality, right? Very similar to linear equation, right? Okay, so from there you see the domain is in interval notation from negative 7/2 up to infinity. Okay, number 23, the function fx equals to square root of 16 minus x squared. Then the radicand has to be non-negative. Okay, now then you execute it yourself. Okay, you do step 1 because that's polynomial inequality, right? So step 1, what's the critical number? Step 2, what is the sign graph? Step 3, that's the solution. And therefore, the domain is 1. Okay, but you need to go through this procedure here. Number 25. How about if fx equals to x plus 1 over x squared minus 9x? I'm sorry, x cubed minus 9x. X cubed minus 9x. It means x cubed minus 9x cannot be 0. Okay, what happened to the numerator terms? Well, the numerator will not give us any issue, whatever x you plug in, right? It's the denominator that gives us some issue if it becomes 0. So we need to set it not equals to 0 and then solve, right? X times x squared minus 9 cannot be 0, and we factor further, right? So x cannot be 0, x cannot be -3, x cannot be 3, right? So the domain will be all real numbers except the zeros of the denominator, except 0, -3, and 3. Number 27. Suppose I have the function fx equals to square root of 2x minus 5 over x squared minus 5x plus 4. What's the domain? So we know that 2x minus 5 has to be non-negative. And at the same time, x squared minus 5x plus 4 cannot be 0. Okay, so x is greater or equals to 5/2. And you will see x minus 4, x minus 1 cannot be 0, right? So x cannot be 4, x cannot be 1. Now, let's take a look on what this is supposed to look like on the number line. It has to be at least 5/2, which is 2.5, right? Yet it cannot be 1. It cannot be 4. Now, putting things together, then we see that the domain must be from 5/2 up to 4, not including 4, and then greater than 4. So now, putting things together, the domain will be from 5/2 to 4, union 4 to infinity. Okay. Now, in my lecture, I believe I have, oh, hold on, I have chat coming in. What if x equals to 1? X equals to 1 will not work. In fact, when x equals to 1, it will make the denominator 0, right? Yet, also at the same time, make the numerator becomes, the radicand becomes negative, right? Yeah. So x equals to 1 itself is already not in here. It's already not in here. When x equals to 1, right? I mean, I exclude x equals to 1, right? But it's already get excluded here. Isn't it mean to be in my notation? No, no, the one I marked is only from 5/2, which is 2.5 up to 4, and then from 4 to infinity. Okay. So x equals to 1 already excluded even from this guy here. Now, things that you need to pay attention, which I will not go over anymore, is make sure you know, make sure you know how to read or how to find the domain and range of a function or relation in general if given the graph. I will not go over this anymore. It's already in your lecture. It's actually on the easy side, but you just need to know how to read it when we have a graph. Okay, so for example, later on, you need to practice the question number 17 to number 20. So practice question number 17 to number 20 in that section 2.4. Okay, also about increasing, decreasing. Increasing and decreasing. And in our textbook, that will be number 33 to 33 and 34. Number 33, 34. Okay. Now, after the break, I will teach you how to, we will focus on graphing, but let's do one more things that also already in my lecture, but I want to emphasize that a lot more, something called different quotient. Something called different quotient. Different quotient of a function of the function fx. In my class, I denote that as dq subscript f is given by dqf equals to fx plus h minus fx over h. Now, this is one very important foundation, cornerstone for your calculus later on. Okay, very, very important. In my class, I will still give you this formula, okay, is what difference quotient stands for, okay. But once you go to calculus, your instructor is supposed to already assume you know what is difference quotient of a function. Okay, now difference quotient of a function has this. So suppose for example, I go a little bit harder right away. Suppose for example, I have fx equals to 2x squared plus 3x plus 5. Then what is the difference quotient of this function? Okay, solution. The difference quotient of this function is given by that f of x plus h plus fx minus over h. Okay, so I will set it up first. Let's find out what is f of x plus h. If fx equals to 2x squared plus 3x plus 5, then what if you replace the x by x plus h? That will be 2 times x plus h squared plus 3 times x plus h plus 5. Okay, now then put this into difference quotient. Difference quotient of the function is on the top left, it's that guy. Oh, you know what? Let me simplify this first. Let me simplify this first. But the plan is this. The plan is this. Instead of putting in into a big function right away, like fx plus h minus fx over h right away there, let's focus on this guy first. I simplify that first. Okay, I simplify that first. This will be 2 times x plus h squared plus 3 times x plus h plus 5. That is 2 times x squared plus 2hx plus h squared plus 3 times x plus h plus 5. Let me give myself more space. And then let me distribute. That's 2x squared plus 4hx plus 2h squared plus 3x plus 3h plus 5. Now, I hope you see what I'm doing there. Basically, I replace x by x plus h into the function and then simplify as much as I can before I put that big chunk into the difference quotient. Okay, that will be 2x squared plus 4hx plus 2h squared plus 3x plus 3h plus 5. That's our f of x plus h. Minus fx, which is 2x squared plus 3x plus 5. Okay, over h. Now then, from here, you need to simplify. From here, you need to simplify. Okay, cancels whatever you can cancel. For example, on the top, you see that 2x squared cancel, 3x cancels, and 5 also cancels. Okay, such that we have 4hx plus 2h squared plus 3h over h, like that. We need to simplify further. We need to simplify further. Okay, we need to simplify further, and I will tell you later on how do we know that we can stop. But to simplify further, I will factor the h and cancel the h. So I get 4x plus 2h plus 3. Okay, so that's the different quotient of this function. Now let's look back on how far do we need to go. So let me write this as a note here. Simplify as much as possible such that if h is equal to 0, we don't get 0 over 0. Okay, so when do we know we can stop? You can stop when, if you replace h equals to 0, you don't get 0 over 0. Okay. So if we look back here, why I didn't stop here? Because when I replace h by 0, at the top I will get 0, the denominator is 0. Then I know I cannot stop there. Okay, I need to find a way to modify this such that it doesn't happen if I replace the h by 0. So after I factor, I still don't stop here. Okay, I cancel and then I stop here. Okay, so Thomas, do we replace the h by 0? No, we do not replace the h by 0. I'm just saying that we know we can stop if we can stop here. If when I replace, so you imagine the next step. You imagine the next step. If you replace the h by 0, you don't get 0 over 0. Okay? If you replace the h by 0, you don't get 0 over 0. If that's the case, then you know you can stop at that point. Okay? Now, I will do one more example, and then I will do one more example and then give you a break. Suppose let fx equals to square root of 3x plus 2. Yeah, we put h equals to 0. When do we know we can stop? We can stop here. We can stop here because when you replace h equals to 0, we don't get zero over 0. Then you know you can stop here. Okay, let's do one more example to explain that idea. To plug in the fx plus h, and so on and so forth are actually not too hard. Usually the hard part is how do we know when do we stop? So the denominator, yes, if what happened if this, we basically do not want to have 0 over 0, which is undefined. Okay, we do not want to have 0 over 0, which is undefined. Anything else over 0 is actually still okay, but you will not see that case, at least not at this level. Okay, what we don't want is this one. This is the one you don't want to happen. When you replace h by 0, h by 0, you don't want to get this. Okay, find difference quotient of that function. So solution. First one, what is f of x plus h? That's square root of 3 times x plus h plus 2. That is square root of 3x plus 3h plus 2. Now, therefore, the difference quotient will be, on the top left, we have square root of 3x plus 3h plus 2 minus square root of 3x plus 2 over h. Now, on the right hand side here, I show you why we cannot stop or why we can stop. So imagine if h equals to 0, what will that be? Square root of 3x plus 2 minus square root of 3x plus 2 over 0, right? But you see on the top, the same thing subtracted, you get 0 over 0. So we know that we cannot stop here. Okay, what should we do then? We will multiply by the conjugate. Okay, so I will multiply by the conjugate of the numerator. So I multiply the top and the bottom by square root of 3x plus 3h plus 2 plus square root of 3x plus 2. Do likewise on the denominator, 3x plus 3h plus 2 plus square root of 3x plus 2. That way, then I can make use of difference of square on the numerator. I get 3x plus 3h plus 2 minus 3x plus 2 over h times that ugly guy, square root of 3x plus 3h plus 2 plus square root of 3x plus 2. Notice that the numerator cancels, right? Some parts of the numerator cancels. 3x cancels 3x. The 2 cancels 2. So we get 3h over h times this guy. Now, can we stop here? Can we say, oh, okay, this is my answer? Then you check. Okay, what happened if h equals to 0? You will get 3 times 0, which is 0 on the top. At the bottom, you have 0 times something, right? But that's still 0 over 0. So no, you still cannot stop there. Okay, now, but you can see very clear that we can cancel the h, right? We can cancel the h, so we get 3 over square root of 3x plus 3h plus 2 plus square root of 3x plus 2. Now then you check when h equals to 0, you will get 3 over square root of 3x plus 2 plus square root of 3x plus 2, which is not 0 over 0. So we are okay. Then we can stop here. Okay. Now that's for this different quotient. After the break, we will learn to graph some functions. But yeah, let me give you a break first. We come back at 9:31. Then if you have graphing paper, please grab your graphing paper because we will learn graphing after this break. Okay, let's go on with 2.5. Keep in mind, even though I don't go over that during my discussion here, But still, you still need to know those material that I already mentioned in my lecture. Okay, from that lesson 6, lesson 7 from announcement 4. Okay, simply because I don't go over that here doesn't mean it's not part of your work of things that you need to do. Okay, I'm slightly behind schedule. I'm basically around 1 hour behind schedule. I supposed to finish 2.6 today. I supposed to finish 2.6 today, but I won't have enough time to finish that 2.6. The furthest I can go today is only 2.5. Now, in 2.5, we learn to graph a function, a 2.5 graph of some functions. Now let's get over some easy stuff first. A function definition. A function is an even function if its graph has y-axis symmetry. And knowing that a function has y-axis symmetry will make our graphing later on a lot easier. Okay, so if we look at the chart, the scheme here, we say that it is an even function by definition if and only if it has y-axis symmetry. But it has y-axis symmetry if when we reflect with respect to y-axis, it fits the graph, right? In other words, if we replace x by negative x, we will get, and y stay the same, we get the same equation. Okay, in other words, if we replace x by negative x, we will get the same function. Okay, therefore, one way to check a function is even, it has y-axis symmetry, is by checking if f negative x equals to fx. Okay, so let me continue from here. So consequently, f negative x equals to fx. Okay, a function fx is an even function if we have that phenomenon. Next, a function fx is an odd function if its graph has origin symmetry. Okay, so let's take a look. It is an odd function if it has origin symmetry. But we know that a function or relation or a graph has origin symmetry if replacing x by negative x and y by negative y gets us the same equation. Okay, in other words, when we replace the x by negative x, the outcome will be the same to the opposite of that y. If we replace x by negative x, then the y will be negative y. So that's how we check if a function is an odd function. So consequently, to check a function has an odd function, has origin symmetry, we replace x in the fx by negative x and show it simplifies to the negative of fx. Okay. Oh, by the way, have you started looking into me going over my the old test, the previous test? Anybody already start watching it from actually from last week, is it right? From last Monday, not yesterday, from last Monday. So I went over plenty of material already from the first, March the 1st, March the 3rd, and yesterday, March the 8th. Okay, I went over a lot of problems from at least 3 different tests. That's not a part of lesson. It's you see the recording from recording from these dates. Basically, my Monday, Wednesday will go over my old tests or my old quiz. Okay, my Tuesday, Thursday is the discussion. Okay, but the lesson is the one I already have on YouTube. We have this talk, I believe, last Thursday. No, actually around 2 weeks ago. Yeah, it's like around 2 weeks ago. Okay. So you see the recording from the Monday, Wednesday class. So far, I already went over almost 4 all test 1. So what you can do is this. Let me just show you that. Give me a second. Let me show you again so that you are aware of what we have. So in the, is it in the announcement? Oops. In the discussion from last Thursday, this one here. Okay, from February the 25th. From February the 25th. So it's more than 1 week ago, right? Yeah, it's more than 1 week ago. I made in the discussion that I will change how I run the discussion. It will affect you Tuesday, Thursday, just a very little bit, but it will affect my Monday, Wednesday a lot more. Now, what happened is that on my Tuesday, Thursday class, we go over problems from textbook, right? My Monday, Wednesday class, I will go over problems from my old tests. Okay, this way then I have nobody can say, but Thomas, the problems in the textbook is different from your test. Well, that's why I went over that in my other class, Monday, Wednesday, that you can have access on the recording also. Okay, your test is 2 weeks from now, approximately. Okay, don't start studying last minute. I put it this way, If you want to study last minute, let's say 2 days before the test, at least what you watch that a little bit first and make sure that it's really easy for you. Okay, so you go to event recording, so you watch the one from yesterday, for example. I believe you have access to this. I'm not trying to save it. Why it tells me to save it? Oh, I need to get the streaming one, MP. You can save it, but so what happened yesterday with them? I went over. Yeah, I went over 419. Yeah, we almost finished this one test. Now the thing is, when I go over my old test, I will get into some questions like even and odd functions. Okay, I think we have that here. Let's see, where's that? I don't go over that because it's I need to go over it in this class first, right? But then here, so let me stop here for a while. So I don't go over with them, the one that I marked with other color, because I didn't go over the difference quotient yet in this class, right? It's in the lesson and it's in the lesson today. So tomorrow, when I go back to my going over my previous test, then for problems different quotient, we can do already. So I will show the work for that. And also for number 7 there. Okay, show that this function is even or odd or neither. Okay, so I will do that tomorrow. This is on the easy side. That's why I believe that's already in my lecture. Okay, lesson 7. It must be there already. And I will go over that again in my previous test tomorrow. Okay, so either you watch my lesson 7 or you watch how I go over that in my test. And that basically the type of function you will see in my test. So do I want to go over that here in this class? It's too easy, such that no, I don't want to. Unless you want me to, but it's just like, okay, if you want me to do anything, when will you do something? Right? If you want me to do everything. Okay, let's do one example then. Let's do one example. So for example, what's that? Give me a sec. For example, is fx equals to x cubed minus 1 over x an even or odd functions? Is it even or odd function? Now, it is possible for a function not to be even, not to be odd. Okay, so it doesn't have to be even, it doesn't have to be odd either. Okay, it may be neither. So solution: how do we check if a function is even or odd? What you will do first is you replace x by negative x. Okay, replace x by negative x. So this is negative x being cubed minus 1 over negative x. You see, either checking even function or odd function, you are checking, you start with f negative x. Okay, so I replace x by negative x. Now then, try to simplify that. And show how it relates to fx. Now here, if I factor the negative, I will get x cubed minus 1 over x. Okay, which is the opposite of fx. So basically, I have shown that f negative x equals to fx for this function, right? Now, so fx is odd. And its graph has origin symmetry. Okay, now let me put it as a note. A function can be even or odd or neither. And actually, it's a challenge if you can find a challenge. Can you find a function that is even and odd? Okay, can you find a function that is an even function at the same time that's an odd function? Okay, that's actually a big challenge. Okay, now once I get this even odd function issue out of the way, then we will start with graphing transformations. There are 4 types of transformation. The first one, translation. You translate, you move it up or down, right or left. Okay, now suppose we have y equals to fx. Then when you try to move it up, down, you have the y equals to the original function fx plus or minus a constant. That's how you move it up or down. Now, for example, fx equals to absolute of x minus 2. Like we know absolute of x looks like a v. We learned that last Thursday. Like this is absolute of x, right? Now, then what happened with absolute of x minus 2? Oh, then we will move it down 2 units. Okay, this is the graph of absolute of x, and the graph of absolute of x minus 2 will look like this. This is absolute of x minus 2. Now, to move left, right, we will replace the x by x minus c. Okay, that will move c units to the right. This is up c. This is to the right c units. Now let's do some example first. Easy one. Can you graph, for example, graph fx equals to absolute of x plus 2 minus 3. Now, the basic function is absolute of x. That looks like this. Now, then what happened to x plus 2? Then you move 2 units to the left, right? You move 2 units to the left. So the vertex origin in 0, 0, now negative 2, 0. Now then, after you move 2 units to the left, you move down 3 units. So the vertex now is negative 2, negative 3. It will look like this. That's the sketch. Now, once I give you this graphing paper, it means I want you to sketch that, to graph that in a lot more precision. Okay, so the vertex origin is 0, 0, move to the left 2, down 3. From that vertex, we follow the graph of the original absolute of x, in which we go slope 1 to the right. Oops. 1 unit to the right, up 1. The slope is 1. It's supposed to go up. Then on the left hand, the slope is negative 1. Okay, that's what the graph looked like. Okay, later on, I think I would just leave it to be on Thursday. On Thursday, where I show you how to find the domain, the range. Actually, we know that range already from here, like the axis of symmetry, x-intercept, and y-intercept. Okay, but for now, we just leave it like this. Now, how about if I change that function instead of absolute of x? Let's change that function to be graph fx equals to x plus 2 squared minus 3. So the basic function is x squared. Then 2 units to the right. I'm sorry, 2 units to the left. And then 3 units down. So 2 to the left, 3 units down. That's the sketch of the graph. Now let's do more detail. The vertex is now negative 2, negative 3. Now, then you remember from the graph of x squared, we have this pattern. From the vertex, 1 unit to the left, right, we go up 1. From the vertex, 2 units to the left, right, we go up 4. From vertex, move 3 units to the left, right, we go up 9. So the graph will look like approximately like this. And the graph becomes a lot more accurate. Right? Now for those important coordinates, I need you to bubble it. Okay. Now from here, you can actually already see that, well, the domain of this quadratic function is all real numbers. Can you tell me what's the range here? Anybody? The range is from -3 to infinity, right? How about the axis of symmetry? Remember, axis of symmetry is equation of a vertical line. It's a line, okay? So the equation of the vertical line is x equals to -2. How about the vertex? How about the vertex? That's -2, -3. So you can see this way. The original vertex is, that's right, it's -2, -3. Originally the vertex is 0, 0, right? Now you move it 2 units to the left, becomes -2, 0, and then you move it down 3 units, it becomes -2, -3. Okay. How about the y-intercept? How about the y-intercept? Yeah, you plug in x equals to 0, right? When x equals to 0, you will get the y is 1. A slightly harder one is how to find the x-intercept. In other words, on this graph here, can you give the exact value for the x-intercepts? What are the x-intercepts? The exact value. We did that work before to find x-intercept, the y is 0. So 0 equals to x plus 2 squared minus 3. Then we solve for x. Okay, so the x-intercepts are -2 minus radical 3 comma 0, -2 plus radical 3 comma 0. Those are the x-intercepts. Okay, so the x-intercepts are -2 minus radical 3 comma 0 for the one here, and this guy here is -2 plus radical 3 comma 0. Okay, if we want to get more details on those. Okay, now that's for left-right translation. The second type. The first type is you move left, right, up, down. The second type is on reflection. We have learned before, if we replace x becomes -x, that's reflection with respect to y-axis. Okay, so y equals to f -x, that's reflection with respect to y-axis. Okay, now reflection with respect to x-axis, the y becomes -y. Reflection with respect to x-axis, y becomes -y. So if your original graph is given by y equals to fx, then the reflection with respect to x-axis gives you -y equals to fx. But that equation is the same equivalent equation to y equals to -fx. Okay, so suppose I have, for example, now this gets into a more complicated case. Graph fx equals to negative x plus 2 squared plus 3. Then how do we attack that? Let's imagine the basic function. The basic function is x squared, right? We know what it looks like. And then we move 2 units to the left. So it looks like this now. Now then, having negative right in front of that x squared, x plus 2 squared, will make the graph upside down. You reflect that with respect to the x-axis. The vertex is still negative 2, 0 though, but the graph already upside down. Now then, you move up 3 units. Okay, that's the sketch of the graph. Let's graph that in more precise mode. So the vertex is now at negative 2, 3. It's upside down, right? So when I move 1 unit to the right, I'm supposed to go up 1, but instead I go down 1. Left, right, 1 unit. Left, 1 unit, I go down 1. When I go 2 units to the right, I'm supposed to go up 4. But because of that negative, I go down 4 instead. Likewise, when I go 2 units to the left, I go down 4. 3 units to the right, I'm supposed to go up 9, but because of that negative, I go down 9 instead. Then the graph becomes like this. Now, of course, from there you can see the axis of symmetry, the domain, the vertex, the range, the y-intercept, and you can compute the x-intercept. Okay, let's focus on the graphing more today. Let's apply this to this guy. The graph fx equals to negative square root of x plus 2 plus 3. What will the graph of this thing look like? And we start with square root of x. The graph of square root of x looks like this. Now then move 2 units to the left. Becomes like this. And then you flip with respect to the x-axis. And then you move up 3 units. So the initial point now, instead of negative 2, 0, the initial point now is negative 2, 3. That's what it looks like. So then let's graph that in more details. The vertex is negative 2, 3. It's supposed to be go up 1, right 1, but because of that negative, I go down 1 instead. 1 down, 1 to the right. 2 down, 4 to the right. 3 down, 9 to the right. So the graph of that function looks like this. Okay, as you can see, the domain is x plus 2 has to be non-negative, right? So it's from -2 to infinity. Now, how about the range? You can find the range a lot faster if you can imagine how the graph actually moves around. And when you see this graph, can you tell what's the range? What kind of y's you can get from this graph? You see the y's actually from -infinity up to +3, including +3. Not from 0 to 3, no, because this actually goes indefinitely far down. It goes indefinitely far down. So the range is from -infinity up to 3. Okay. Furthermore, how about the y-intercept? So we see what is f0. F0 is -√2 plus 3, or we can write 3 minus √2. So the y-intercept is 0, 3 minus √2. Okay, so this coordinate here is 3 minus √2, 0, 3 minus √2. And from that graph, you see that the y is between 1 and 2, right? The y is between 1 and 2. Means when you use your calculator and compute this, it will be 1 point something. You can try. You can try that. You can try that. Okay, use your calculator to compute that. Now, how about the x-intercept? To find the x-intercept, we set the y equals to 0 and so for x. Square root of x plus 2 equals to 3, x plus 2 equals to 9, so x equals to 7. X-intercept 7, 0. And you can see here, it happens to be one of our special important coordinates, right? 1, 2, 3, 4, 5, 6, 7. Okay, so the x-intercept is 7, 0, verified by our graph and done algebraically. Okay. Now, actually, I want to go one more step further. So what happens if we want to graph fx equals to negative square root of 2 minus x plus 3. It's 2 minus x, not x minus 2, not x minus 2, 2 minus x. Which, if you think about this, this must be coming from reflection with respect to the y-axis. So originally, the way you think will be like this. Can you graph square root of negative square root of 2 plus x plus 3? Notice that this is just the same to negative square root of x plus 2 plus 3, right? That's the graph we have above. It's this one. This is the graph. That's the graph. Now, imagine if you replace the x here by negative x. Imagine if you replace the x there by negative x. Replace the x there by negative x. That becomes 2 minus x there, right? But replacing x by negative x, that's reflection with respect to y-axis. Okay, that's reflection with respect to the y-axis. So what happened is this, that we already have this guy here. That's negative 2, comma 3, like this, right? That's negative 2, comma 3. Now, when you reflect that with respect to y-axis, then that starting point, negative 2, comma 3, will be reflected here, right? You reflect with respect to the y-axis, right? It goes here. So instead of something looks like this that we have earlier, instead of something look like that, when you reflect this graph, you will later on get something looks like this. Okay, now let's put that into more detail though. Okay, let's put that into more detail. So that's the new starting points now. I go down 1, left 1, go down 2, left 4, go down 3, left 9. So that's what the graph looks like. Okay, now in the last 10 minutes, I will go over something called deletion, the third type of transformation called deletion. Is it deletion or dilatation? I think it's dilatation. Let me check my English. Give me a second. Apparently, I forgot to record, and I don't remember where I forgot to record this. I think after the break, I forgot to press the recording. I will not go over this again anymore though, so please take a look on the notes. Okay, the one that I post on the discussion board. Okay, and so that you can see what is being done actually with the part that I didn't record. Okay, but I believe what I went over here is actually already clear from my lecture in lesson 7 in announcement 4. Okay, so once you watch that lecture, compare that to these notes and try to go over that on your own. Okay. Yeah, but I will save this and post it on the discussion board. Let me show you where I put it. Let me save it first. Let me save all of them first. Give me a second. This is math, Tuesday, March the 9th. That's on 2.58. We have 2.4. 2.4, I believe it was still recorded. 2.2b, the leftover from last time, 2.2, it was also recorded. The one not recorded was 2.5, 2.58. But again, I believe my recording from announcement 4 is pretty clear already. Just look at these notes and then compare that to your lecture. Okay, I posted in the discussion board. At least you get access to the notes though. Okay, I will put it here. I have been doing this. It's not only this is the first time. I've been doing this for every one of my discussion. So if you see the discussion board from the past, after the lecture, after discussion, I actually post the notes on that discussion board, such that if you watch it later, you can print that out first and use that as your note. Okay, and of course you can always put extra notes on the notes I give you. Okay, now I don't remember when I really paused the recording and forget to continue recording, but one of the things that I don't want you to miss is that I already went over a lot of material from my previous test. Okay, and you can see that from my Monday, Wednesday class. So if you go to the discussion and you go back to the one on Monday, Wednesday, let's say the one yesterday, right? Monday, Wednesday. Okay. So in that class, we went over 419 Math 2 SMC Test 1. Okay, now, and if you go back further, the one from last week, I think that's Monday, Wednesday, March the 3rd, you will see that I went over spring 17, fall 17, spring 19, spring 19. In fact, if you go back even further to March the 1st, if you go back even further, March the 1st, you see we went over some of these already. Now, of course, when I went over those tests with them, I have the recording also, which you can have access. You can see from Confer now. Event recording. And for example, the one yesterday, right, from March the 8th. You can see what we did there in the other class. So you choose MP4 streaming. If you want to download it, you click this one, the one with that roll there. Then you click that one if you want to download that video. But if you just want to watch it directly from your phone or from computer, you go streaming. And of course you play it. Okay, so I went over those test questions in the past. Okay, actually I start from the beginning of March, March the 1st, and then March the 3rd, and March the 8th, and tomorrow, March the 10th, I plan to finish one more test or go over the leftover problems that we didn't finish last time. Okay, see you then.
Yes, sir. Thanks, sir.